and he's on many different AI projects, including some AstroAI projects. And today he's going to tell us about understanding fundamental release of AI within synthetic experiments. And I guess I'll just say that he's going to tell us about how generative models actually try to learn things. So, Corey, thank you very much.
Okay. Does this camera have me if I go here? Okay, hi everyone. So my name is Corey. I'm a grad student in Harvard Physics. Today I prepared this talk to kind of like really understand like what fundamental abilities AIs do have, what kind of they like lack. Yeah, and I think it's going to be a rather easy talk, not a single equation, maybe one actually. So AIs, we're in this world where in this world since 1980s, there's always like the skeptic side of AI, like this is not going to work, it's hitting a wall. And then there's always like a proponent side of AI, which is saying that like general intelligence is almost here. I'm not here to like take a side, but it seems like recently I think we all agree that AI has been showing like immense progress. Like they're solving like PhD level questions, and those math questions like I get like maybe like 10%, along it's like 83%, right? And recently people also tried to test it with this thing where you need to see a few examples, and I think here basically you need to put every block of color as up as their heights. And then you need to like generalize the new input just by learning from these three examples. And OpenAI's one reasoning model, like the accuracy, this is like the base here of the x-axis, and then the accuracy suddenly really went up this January. So people are saying like deep learning is hitting a wall, but it's hitting it vertically and just going up. So yeah, so this all looks impressive. But then like there's always a criticism. Yeah, but didn't they like train on the whole internet? Didn't they just see all of this? So what I said recently is I took a South Korean college SAT. And for those who don't know how this works in South Korea, they take it very seriously. The professors who make these exams are literally locked up in a cell. Because if this like gets leaked, South Korea has a huge problem. So yeah, and then I tested the O1, which couldn't have trained on this. And then it achieves like level 1, which is top 4% of South Korean students. But there's still like criticism saying that like aren't these problems extremely stereotypical? Every year it's kind of like the similar vibe of problems. But then one interesting thing is that this is actually same for the students. Like the students also see years and years of these problems, and if anything, for 2 years they're like this is kind of the problem with the Korean education system, but they're trained to really just like crush this one exam for like 2 years. And AI did this as well. So I know this phase where AI is definitely intelligent to some extent. I just like accept that. But then like it's kind of definitely different than the intelligence we know of like humans and animals. So how can we understand this? Yeah, so I think there is kind of this like I come from a neuroscience background. I think there is kind of this trackability and cognition trade-off, where in general, the more capable that intelligent agent becomes, like the less trackable it is. Because I used to work on like this small worm called C. elegans. That's like very easy. You just have thousands of worms. You can almost treat each worm as independent sample and just average over the data set. But then when you go to monkey and humans, like my friends who are researching in those fields actually need to care about, oh, this day the monkey just felt sad. It didn't want to do the experiment. They need to deal with these like internal states, which are kind of like hard. And now that one thing is which is kind of amazing is that AI is like relatively more interpretable than like biological brains. But then at the same time, they really like came up this cognitive capability axis. So it's really exciting to like understand these as kind of a neuroscience system. And like this trade-off exists in AI as well. Like you have simple linear regression models where you just like understand like the theoretical solution. And then you have models which you can kind of interpret. And these models which are kind of like they have to involve the best mathematician in the world to really understand what's going on or even like evaluate their performance. So like there like this trade-off exists in AI as well. So me and my group's like approach is can we do like science on models roughly within this ballpark of like hard-ish problems. So yeah, so we call ourselves the program of physics of intelligence, and today I'm just gonna like get into like 2 works we did. So general, our approach is to design small synthetic experiments to probe fundamental capabilities. I'm gonna go through two, which is, the first one is compositional generalization, the second one is in-context learning. The first one is the ability to learn concepts, individual concepts, and then compose them together into new combinations. So this is like a highly intelligent phenomenon. For example, people can draw a red dolphin, in this case actually AI drew it, even though red dolphin never exists in the world. But we understand that like the concept of red dolphin is just like you just need to color the dolphin in red. And you can also like do these things where as a non-native speaker, like I say this a lot, like, yes, I teach this class. It's like wrong, but then I just use compositional generalization instead of memorizing the whole set. Bird plus ED means probably pass. That's what I did. It's not always right, but then like it roughly works. And AI has been doing this recently. So astronaut on a horse, it was able to like draw this picture where astronaut is riding a horse. People are a little bit skeptical after a few years, this is 2022, that like maybe now that's in the training set, so you try to force an astronaut, that also kind of works. This is all interesting, but then like we really want to get down to the fundamentals of like, can it really do this? Like, can we like really train this in synthetic environments? So we have a simple task here where depending on the label, so one means circle, and then A means red here. So what is 2B should be? For human, it's rather easy that the human will very quickly figure out that what should go here is a blue triangle, given these two concepts. So what if we train the models only on these combinations? Will generative models, the review models, be able to generate like this blue triangle? That was the question we asked. And then the conclusion was that it was possible. So here, actually, sorry, here there's another concept which is like size. It's not just shape and color, but it's also size. So you can like generalize. It only sees like these combinations, and it can generalize to other combinations of the individual concepts. The natural question, which actually is really important to ask, is that like to track what it's doing. So when we ask for like the small blue triangle, the model during its training dynamics learns some things like shape before other things like color. So this is like a real image generation model. And you can see that the model, when you ask for blue square apples, as you scale up the model, what happens is that the model can first draw apples, and then the model can draw blue apples, and finally it can draw blue square apples. And this is actually interesting if you think about it deeply, because there's no reason the model could have went in the other way in the context space. Why couldn't it gone this way, where it generates a square apple first and then makes it blue?
So, sorry.
Yes.
With model scaling, do you mean sort of number of parameters in the model? Is that?
Yes, here it's number of parameters. In general, like people think it's like also fine to like just think of that as like trading dynamics, but it's just that like for a single model size, there's kind of a best, given a compute budget, there's a best size you can use. So these two scaling axes are like trade-offs between them. And in fact, like in our experiments, we observed this kind of like behavior as we train the model more. Yes, so what determines the speed of concept learning? Like whether you learn shape first or color first? So we kind of like observed the loss of the model. The model is quite literally optimized to like reduce the error on the prediction of the image. So we define this thing called concept signal, but then like I think this is the most intuitive way to like think about it. So if I define red as purplish red and blue as purplish blue, even if I give you the color label, you can only reduce the loss by a little bit because they're too close together. But if this feature is like strong, red is very red and blue is very blue, just by knowing the label of red, blue, you actually have a relatively bigger gain in loss because you're kind of, this feature is more salient in your data set. So we run experiments where we control for this, like how much color is important in the data generating process. So we train a model again. So in this case, like we actually substituted shape with just size because like it's easier to define a continuous variable. So we train on big red circles, big blue circles, and small red circles. And this is a training set. And first of all, I'm gonna show what happens if you tell the model to generate a big blue circle. This happens. So the color coding here is that blue curves are model training trajectories where the color was not that important. And red ones are the ones where color was very important. So what happens here is that if the color is not very important, so again, we're asking the model to generate this. What happens is that initialization is kind of at 0.5. The model first learns to generate size first, like to get size right first. And then it learns how to get color right. But when color is important, then the model optimizes for color first and then size. Now, okay, this is fine, but then like at the end of the day, you train for long enough. This is a training distribution, so all models will actually like get here successfully. But what happens out of distribution now? What we're interested in is generating, can the model generate small blue circles? So here, interestingly, we see that when color is not that important, what happens at the beginning is that the models, it needs to go here. The target is 1, 1, which is small blue. The model, at the cost of getting the size right, it gets the color wrong. So here's the target, and then so it goes up left, which means it gets the size right, but the color wrong. And then it suddenly turns. It shows these like turning behaviors and then goes to the right target. Interestingly, when you have like the color concept signal, which is like actually big, then what happens is that the model first goes the other way around, where it gets the color right at the cost of getting the size wrong, and then shows a sharp turn before going to the right target. I'll only go through very briefly because like there's more stuff I want to talk about, but what we actually found out is that like whenever these turns happens, the model actually at this point exactly learns how to manipulate the two different concepts individually. So you can actually go into the model's like internal representations. And then what you can do is that you can push the model's like internal activation into certain directions. And that's what we call controllability. Can you control the model by intervening into its internals? And what we see that all of these models can actually generate small blue circles after the sharp turn. But some of them like don't show the behavior, which I have to say that like if you train like 5 models, some of them will seemingly fail, but then after the sharp turn happens, all of the models are actually capable of generating the small blue circle. We can come back to this if you have more questions. I understand it might be a little confusing. But yeah, but for now, I'll just go to jump to the second concept, which is like in-context learning. So in-context learning is this interesting phenomenon which was like hard for models for a while, until like a few years ago. So given these sets of input and outputs, what should the output be for this input? And I think for a human, it's pretty easy after staring at these images for a while that, oh, probably what I need to do is to fill in whatever is enclosed, totally enclosed. So you probably need to just put in yellow in all of these cells. Humans are pretty good at this, but then for a while, models were pretty hard at doing this. But then recently, large language models like ChatGPT, they're actually amazing at in-context learning. If you have a new language like that it has never seen during the training data, you can just push it into the model context, a bunch of text coming from that language. And then it can kind of like learn how to like articulate stuff from in that language. And then one thing in the human analog, one thing interesting which happens is that humans are capable of doing in-context learning, but kind of unconsciously. So this experiment by Tim Burns labs is interesting, where the humans are shown a sequence of images. You flash a sequence of images on humans, but then underlying the generating process, there's actually a graph navigation going on. So the images are not completely randomly shown, but then there's kind of a chess player moving on this grid, generating images. And what happens is that you can take the fMRI scans of humans, and then actually like kind of like you compute a distance metric on the fMRI scans, and then you can actually reconstruct the graph, which is the data generating process. The interesting thing here is that if you ask humans, do you think the images are random? In a lot of cases, they think that, oh yeah, there doesn't seem to be any pattern here. And they are actually like unable to say that there's kind of an underlying graph, even though they're able to perform. So we decided to run kind of a similar experiment, give a totally new task, which is kind of like almost like odd, because that task was very odd, just like showing images in kind of a graph navigation. So give a very odd task to LLMs and kind of see if their internal representation do something.
Before you move
Yes.
on, can you go back to this? So what was the task here for the?
Yes. So, oh, yes, I should explain that. So the task is actually for the human, task is a little bit different. There's like a different classification objective because the humans always need to like, you need to actually give a human something to focus on. So they give a different task where they need to classify some images or memorize. Actually, it's not that important what the actual task is. But then like here, what's important is that in order to perform any arbitrary task, humans form fMRI like in their brain states, representations which kind of like mimic the data generating process is what's going on. But then the actual task is something like irrelevant. I forgot the name, but then it was like a task which is probably just say like, is this a tool? Is this like classifying these images? Some task mostly irrelevant of the graph navigation task. Yes, so in LLMs, what we did is that we put random words, 16 random words on a grid. And what we did is basically the same thing. We made a player navigate on this grid randomly, just a random walk on the grid. And then on each case it steps on, it just generates a word. So this is what's given to the language model. And then actually in here, like for language model, we actually don't give a task. We don't ask the model to do anything, we just give this and then like make the model generate. And then so what happens first is that like the model can actually generate successfully following the graph structure. So it doesn't randomly here, so the last word here is opera. It doesn't randomly pass to mass or just says anything else about opera or just tries to talk to the human. It actually successfully generates either plain, egg, or manual. But so that's already shows that the models can perform a totally new arbitrary task. But then what's interesting is that as you give it more and more, the context length is the number of entities you give it. As you give more and more of these like words, the model's internal representations actually rearrange to mimic exactly the structure of this graph. So here's the GIF. Yes, so as you trace on the graph, you're doing random walks and giving this as a context to the model. The internal representation form this basically reconstruct the grid inside the mobile internal. So this is just a PCA of the mobile's internal representation.
Are you showing the model
Yes.
the grid?
No, so the model can only input text. So I'm showing the model exactly this.
But you're
Exactly
showing
a sequence of words which has been generated by random walking on the
so
grid.
you showed many examples of the.
Yes.
Okay.
Yes, and then I'm not training for anything. So you can just like try this yourself. Just generate a long like sequence of words on a grid and then just input it into ChatGPT. It'll probably be able to like generate words respecting the grid structure, even though you didn't explicitly tell it that there is a grid structure there. But then the mobile internals, just like humans, the mobile internals actually know that it's a thing. Okay, so our hypothesis here is that the model internally implements some kind of energy minimization, where it kind of sees different entities and it tries to minimize kind of the entropy. It tries to put nearby entities seen together, close together in representations. So actually, like that metric, which is called energy, like decreases, and then when the energy hits some point, the accuracy on the graph navigation. So the accuracy is defined as did you like successfully predict a graph neighbor. That's kind of what we define as accuracy. Accuracy like sharply rises after the energy has been decreased. Yes, so now we know that models actually they can perform in context learning using task-specific representations. So these are like two phenomena we kind of like study using synthetic, small synthetic like experiments. The models can using only like a part of the data, which doesn't span like this small blue circle, the models can like figure out that there are different underlying concepts and compose them together. And the speed which they do so, or the order which they do so, is just determined by which one was more salient to the training data. And then the second one is in context learning, where the models can learn a totally new task, without any extra training on this specific task, just by giving it as a context. Now actually, so I added this section because recently there's been so much interest in like mobile's reasoning abilities, their abilities to like solve problems which are harder, which they almost like need to fail once or twice. Yeah, so what other fundamental cognitive abilities remain? So for a while, people thought that models are not able to reason. So this is a game called the game of 24, where you're given 4 numbers, 1, 2, 3, 4, and you need to use the arithmetic operations to get to the number 24. And you can only use each number once. And I think in this specific instance, it's actually pretty easy. You just need to multiply them all together, and then you get 24. But then you can have like different combinations of number, which are more challenging. And then like people also said the models are actually not able to learn in some sense. So this is actually a little bit ironic because we're teaching models by training them on vast amounts of data, but it's actually hard to teach models a single short sentence, which I'll get to. So first, I'll cover reasoning. So recently, people have shown that reasoning might be actually much simpler than what we thought. Actually, to implement in models, true reasoning is a little bit of a philosophical point, but one thing this is already a knowledge update in the field, that we thought that reasoning is this really hard ability that humans possess and like models are fundamentally unable to. But then recently people just showed that like you just show some data, show some reasoning traces, which means that like if I need to solve this game, just put it in the training data where I tried to solve this game, failed, and I literally say, oh wait, this doesn't work. I should go back to the initial state. Just put this in the training data, then the model can actually do it and also like generalize it in different cases to even like different math problems, and then apply it like out of distribution of not just like this card game, but then in different math questions where you might fail. So yeah, now people are saying that maybe the only thing you need to do is just train on some reasoning traces. But then yes, of course, like it becomes a philosophical debate of like whether it's cheating to actually put in reasoning traces. They should have developed it themselves, or that's kind of a hard one. And then learning. I think this is actually one of the hardest problems to tackle AI. So like, let me define addification as x plus y times y. And then probably most humans can actually answer what is 3 addified by 4. They just input 3 and 4 into this formula and then like get the result, which I think is like 3 plus 4, 7 times 4, 28. And then it's very probable that if you just ask a human to do this like multiple times, and then like come back in like a month, and then say, oh, can you addify 1 by 2? Well, they either didn't memorize this, or they can actually like perform it. But the interesting thing is that if it's like important enough, if this operation is just like important enough, it probably is not. But if it is, humans can actually internalize it using a single sentence. But it's actually pretty hard to train models this way. If you just have literally this sentence, it's very hard to just like fine tune the model on this single sentence and make the model successfully use this function. So this is actually very hard. So the ability to learn itself is actually not present right now in models. And on the same thing, there's like belief updates. So Trump launched the meme coin. If you ask the ChatGPT, like, did US president ever launch a meme coin? It says like, no, that wouldn't align with the typical activities. And then it says it's highly improbable. While we live in unpredictable times, this scenario remains far-fetched. Until it searches up, maybe you search and then it realizes that this is possible. But then like it's actually very hard. So if you fine tune on Donald Trump did launch a meme coin called Trump, if you fine tune the model on this fact, the model still, if you ask for did the US president ever launch a meme coin, the model is very inconsistent. It still isn't able to just say that, oh yeah, this happened. You actually need to train on a lot of data having this, which are like follow-ups of what happened here, for the model to realize that this is a reasonable thing to happen in the real world. So belief updates are hard. It's actually very hard to update the model with real-time new knowledge.
I would argue that it's hard for
Yep.
anyone to.
It's hard
anyone to accept that.
Oh, this specific one? Okay, this specific one is, yeah, it's actually pretty challenging even for humans to accept that with a single news, but yeah. But in general, I think humans are faster because I trained models on like, actually, this specific thing I'm like investigating into this as a research. I'm trained the model on like 100 follow-ups of this statements, and then the model still can't. It just believes that this is like totally unreasonable. It's very hard to update the model's belief. Okay, now actually, and then to come to the second one, let's actually play a game. So, any volunteers? Do you want to volunteer?
Yeah.
Okay, so let's play a game. So
You're not gonna do anything bad to me, right?
sorry.
Nothing's gonna happen to me.
Nothing bad is gonna happen.
Okay.
Nothing good either.
Can't even happen.
Yeah, okay, so one of my hands, I don't know if the Zoom can see, but one of my hands, my left hand or my right hand, is gonna contain a reward, okay?
A reward.
So we're gonna play this game multiple times. No real reward, but just assume it is a real reward.
Okay.
Yeah, so you just need to guess where it is. So game one. Okay, you got it wrong. If it's right, I'll do a thumbs up. Okay, game two.
So do you actually think about which one?
You try to maximize the reward.
Okay,
That's the least thing I can tell you.
okay. This one.
Right. Game three. Wrong. Game four. Wrong. Game five. Wrong. Game six.
What's my reward?
Right. Game seven. Right. Game eight. Right. Seems like you figured it out, right? So what's going on here is that the reward, like I didn't tell him, but the reward is in fact alternating. The reward is alternating between left, right, left, right, left, right. Interesting thing is that ChatGPT, you can solve like really hard math questions. If you just do this interaction with ChatGPT.
Can I see it?
Yes. Thank you so much for participating. Yeah. So Rocco just did something like one of the strongest AI mobiles can't actually do, which is like, and Jan LeCun like posted this like famous tweet called like the LLMs currently are dumber than cats, and people are saying like they can solve all these hard math problems. Can your cat do that? Like, what do you mean by LLMs are dumber than cats? This is actually an example where LLMs are indeed dumber than a cat. Behavioral adaptation. So this is like largely missing in large models. So if you ask GPT this, it messes up one time, so it switches, and then it messes up again, and then it switches again because the reward was not there. It never figures out that, oh, actually what might be going on is that it's alternating, and I'm just on the wrong phase. So adaptation and efficiency, I'll come back to this. So yes, this is actually a neuroscience experiment, which I was actually inspired to this from a neuroscience experiment. You put a mouse in this like virtual rig where you can't see it easily here, but there's like only two passes here. You can either go here and then go to the left or to the right. And then the reward always alternates left, right, left, right. Even if the mouse gets it wrong the first turn, after multi-turns, realizes that this world, for some reason, it's put it in a world where the sugar water is doing left, right, left, right. Even though, of course, nature never gave this weird, very weird artificial task of left, right, the mouse can adapt to this. But then models actually don't realize their multi-turn behavior, and then like they don't. So I think the right way I put it is AI, like even though they're very good at problem solving, I think they really like overfitted on solving a well-specified problem on one go. They're actually really good at that, but they are actually not very good at adapting to a given environment where there's some uncertainties that you don't know in a prior to the exposure. This is another thing, efficiency. So if I give this task where there's like a bunch of edges, so I can promise you this works, but just because of the time, I'm just gonna put them in a visual representation, which is cheating because models might do this internally, but like they can't draw something. So yeah, so if you put all of this in a visual representation and you ask, how do I go from 31 to 10? Then you should say 31, 2, 4, 9, 10. Okay, but now imagine this task was given only as text form. So, and you need to like find how to get to it and so it might be the case that at first you try to like start from 30, try 8, and then, okay, 8 is actually the lucky one, but you can go wrong. You can go for 50 here, and then 15, and then realize that 15 goes to 44, and 44 goes nowhere, so that's not a good way. And then like backtrack multiple times, and then figure out that the solution is indeed 38, 3, 45. But the interesting thing is that if you give this task multiple times to humans, what happens is that humans just realize that all these graphs I'm given actually have this kind of structure. So the easiest way here to actually solve this task is start from the end. Where is 28? Go back to 35, 35, 44, 44, 0. So it must be 0, 44, 35, 28. So like going backwards. The interesting thing is that, yes, so you give this multiple times to the AI, like they can solve it because what they say is that, oh, I've seen this problem. I'm going to use breadth first search, which is this well-known concept in computer science. It just applies this forever and never realizes that the distribution it's being exposed to, there's actually a much easier solution. So they are really not trained to be efficient. So this one actually even O1. Yep. This is
So I'm a bit confused because what you
Yeah.
showed before is that a model, much before, is that a model can actually get the geometry right? At least it can reproduce a grid. So is it not doing that in this case? Is it just memorizing but not putting?
Yes. So I think this is like the very like confusing part of modals is that they have some level of adaptation, but not some level of adaptation. And that's kind of really hard to understand because like they definitely have some level of adaptation. This is why people can build frameworks where there are like frameworks which are trying to solve coding tasks. What they do is they put two AI agents together. One AI agent tries to solve the task, and then if it makes a bug in the code, the other AI agent just like reads the whole process and says, oh, looking at a high level, you made this mistake, retry, and this makes things better. But then like, so like they are definitely able to adapt and understand what's going on in long context, but then they're actually not able to behave this way, which is very interesting. Which actually like, I'll go back to actually this task where we're playing the game of left, right. The interesting thing is that if you actually just like scrape all this chat history and then reformat it and put it in one message and then you cast the exact same problem this way, that here is our two players playing a game. This player A is trying to play this game and then like show that player A like failed multiple times because they got the phase wrong. And then ask ChatGPT like, why is player A failing? And then ChatGPT can actually pose it as a math problem and then like solve it. Oh, what's going on here is probably that the data generating process is alternative, blah, 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 I can solve it. So interesting thing here is that the model is the same problem. It can solve it when given as a problem set, but it cannot solve it when it should behave that way. So that's kind of the interesting part where these modal adaptations are actually like very unstable. Sometimes they work, sometimes they don't work. And it probably has to do with the fact that like it's only being optimized for positive rewards in a supervised fine tuning, and it can't do in context reinforcement learning. So that's kind of the more technical version. But then yeah, it can't really learn that well from multi-turn interactions. Is I think the conclusion. Also, the task actually was easier for the modal, the graph navigation task. Yeah, so this is a concluding slide. So I actually believe that intelligence could be small because like, I'm not a skeptic, but like our DNAs are really tiny. And one thing interesting about humans is that like, if you take a human from Stone Age, like a lot of people believe that the modern human is actually really smart compared to like the Stone Age humans. The interesting thing is that if you actually bring one of the Stone Age humans and grow them up in modern society, they'll be right here, like coding Python and then like talking about AI right with us. That's kind of like interesting. So really there's like not that much, which is like hard coded in us. So like, yeah, also like our processing speed is so much slower than LLMs. So I believe that once we like understand all these fundamental abilities, one day like intelligence can like really be like small. So yeah, that was it. So this is kind of the people involved in the research. Thank you very much.
Hits per second, that's our nearest processing.
Yes, internally. So like you get a lot of input actually. A lot of input from the visual stream. It's like very high resolution, but your brain actually throws away most of it. Like, yeah. The brain throws away 99.999% of the information. Only 10 bits make it true. Okay.
That was very interesting. Thank you very much. Questions, comments? Yes, and Tara?
This might be a bit speculative, but I think I was wondering, so in the context of both tasks, the grid-based one as well as the left-right one, it looks like the issue is that it's not able to form like this latent or infer the latent like model of what's happening in the left-right one. So I think more generally, I was wondering, are there obvious trends in which tasks or which settings it is able to infer the latent model of what's happening and when it's not able to do that?
Yeah.
In the grid context or
Yes. So I think getting a little bit technical, I think the issue is actually like pretty simple. It gets a little bit the technical of well, how these models are actually constructed. So these models are actually like constructed by like, well, I don't know about ChatGPT, but most models are actually constructed by training on like how to answer a question well. So they're trained on a bunch of like the user asked for this, what is the right answer to give on single term preference data sets. I think it's literally that, because like if you give the whole question in a single turn, the models has been optimized and they're in general very good at generalization in all sort of domains. So like, they can answer single turn and the single turn questions very well. But I think they simply haven't been exposed in a multi-turn scenario and have been trained on like user assistant, user assistant, user assistant. Now what's the best thing to do? They just, I think it's like as simple as they just haven't been exposed that much to that kind of data.
What was that?
You remind me of this.
Oh, yeah, well, yeah, I'll do that. So before you leave, sign off your name there. Not that you have to leave now, but we need to keep control. Who's eating sandwiches? Any other questions, comments? Yes, Axel.
Yeah, thank you very much for that. That was really interesting. Do you know how good those models are, especially like multimodal models, for example, at solving jigsaw puzzles? Jigsaw puzzles. Are you aware of any experience? Because like recently I was watching my 2-year-old starting to solve jigsaw puzzles. I thought I was really impressed. Okay, yeah, she's really picking up really fast. But I would imagine that even like for these models, something like this must be possible.
Yes, yes. So
it's very hard.
yes, I think so. So jigsaw puzzle. So right now, yes, a lot of like kind of the reasoning research is done on just like language models, and jigsaw puzzles is like a highly visual task. But then, yeah. So I think I think it'll be very easy to develop a model which will solve jigsaw puzzles extremely fast. But it's gonna be like a specific model, which is like specified to finding patterns, and then you're probably way superhuman in finding like and memorizing all the edge shapes, and then like cross-matching them internally. You're probably like training a specific model for that, they're gonna be really good. But they're currently like, they're very bottlenecked by the ability of visual understanding of models, of integrating the reasoning part and then kind of the vision part, which they naturally have. That kind of area is actually not as fast developing as all the other abilities.
So this is an AstroAI talk, so I guess we should talk a little bit about Astro. So in terms of, so you showed all these examples where like the models try to learn the sequence, the large language models, or even if you pass a sequence that is geometric as text, it will eventually generalize it. So for tasks in astronomy that involve both language and numerical objects like data sets, what is your view on what is the best way to help models generalize about tasks that an astronomer would normally do? For example, fitting an SED spectrum. Do you think that these models are now able to take, say, you're trying to fit a spectrum and you get a fit, so the human would say, well, you should increase the star formation rate in order to fit this particular task, and then passing the data as text. Is that an approach that you see as plausible? Because I would think of the other approach would be aligning representations from the data and the text, and then try the model to learn a shared representation of these two things. So how do you see this, plugging into tasks that scientists do, like, spectral fitting, et cetera, et cetera?
Yes. I think that's like the question. I think like the way I think of it is, yes, I mean, I think there's definitely two ways. I think like if I had to do that right now, I would definitely just totally not use LLMs, just like develop a specific model which takes numerical inputs and does something which I understand correctly. But then like the other way to feel this heading, especially like these big companies is thinking of, is like really just like make these models understand the human action space. And then it's not like humans are perfectly able to, once you see the plot, like transfer the numerical values. You're also like highly relying on like we kind of like take the numerical values and project it into kind of a qualitative space we can reason on. So like I think a lot of these like companies and like AI researchers are really trying to like give them tool usage. So make them do the same thing humans do. Like anything involving like actual careful numerical calibration, outsource it to a different tool. And then like people are actually working on like making models just like people are saying like it's really bad that we're training these models just to do 3-digit multiplication by feeding in all the combinations, making them learn that. Like they should just be allowed to like a calculator. So I think like in the long term, that's how I see it's going, where the models like the input will be the same as humans, just like text and images. And then the models, however, will be able to use tools which are more specified. And in fact, like people are now already like already showing that models can actually like build reasonable tools. And they're at the preliminary level, but like they can build like tools for data analysis specified for each problem. So yeah, I think that's kind of the long future. But if I need to do it right now, definitely a specific model.
Thank you, Corey. Okay, any other final questions, comments?
I think I had one question. It's Wazoo.
Oh wait, I hear something on this. Oh, maybe it was just you. Oh, I heard something from my.
Oh, is there
Yeah,
something
I
on-
mean, I think I probably have one question.
Oh no.
Someone's trying to speak, but we can't hear you.
Oh,
I mean,
can you put it on the chat, please?
Sure.
Maybe. I can't hear something.
oh yeah, sorry.
So should I speak up or should I put it in chat?
Speak up.
Okay. So let's say, like for example, when we want to do like parameter-based inference, we use like different simulation tools like for through which like we train a neural network and then try to do like parameter-based inference. Let's say, for example, from protoplanetary disks, we might like train on Fargo simulations and then try to like get like do parameter inference on like real data. So I was wondering, like, could these methods be extended such that without training, like if I want to like let's say test on like a new set of simulation tool, I probably have to like retrain the model again, like in a regular way, if I were to do it in a regular way. I was wondering like if we could kind of generalize the model such that without seeing like simulations from like different simulations, if we could predict parameters without like explicitly training on a new set of data. I mean, I'm not sure if I could
Yes,
like
yes.
convey that.
No, I get the question, and you're talking about training specific models, right? Not using these huge models, but training specific models for.
Yeah, exactly. Mm-hmm.
Yeah, I think, yes, I actually don't know how much like the concept of meta learning has been like studied in like parameter inference. So meta learning is this concept where you explicitly teach the model not to like just predict something, but actually like predict something given that the current distribution is this. So it's more so like it's imagine you shuffle all the MNIST labels. So for example, for like 3 you need to say 7. One, like obviously if you just like feed in a huge data set where different parts of the data has been shuffled differently, the model gets like chance accuracy because you shuffled it randomly. But then if you do this thing where at each trial, models gets 20 examples of the current label to image mapping and then predicts it on the last one, like then the model can actually do this. And this is called like meta learning. But then what people showed in language models is that you don't need to explicitly construct this meta learning objective. It can just like emerge once you have like enough data diversity. So I think that's going to be the same question here. It's always going to be the fight between like, okay, let's just train one model, but make the data diverse enough so that like it's just going to generalize to some other simulation code, or explicitly train it with a meta learning objective where the prediction should be always like conditioned on few examples given at inference time. So yeah, I actually, yes, I actually don't know. It's kind of like, I'm kind of curious like how much people tried meta learning, explicit meta learning objective in for different code bases.
Okay, any other questions? If not, this Corey again, thank you so much. Your name, and don't forget to put your name in favor of the back. Thank you so much. Thank you.